Alright, so let's start with this example 938. This example is about this function. We have already seen this. It's the square function, ordinary square function on R restricted to this interval. And the thing that we already know about this function is this. We know that f is 0.1 close to 4 near 2. We also know that this does not happen for the entire function if we need to restrict it near 2, but then it becomes 0.1 close to 4. Also, one can reduce this number further. F is 0.01 close to 4 near 2. So to show this, to show that this is also true, you need a new value of delta, a new one which is different from the previous one. And you can verify this, that if your x belongs to this interval and the distance between x and 2 is less than 0.002. I think we need 2 zeros, yes. Then the distance between f of x means x square of course, and 4 is less than or equal to 0.01, that is f is 0.01 close to 4. I leave the actual calculation to you. Okay, so it's just a fact that the author is mentioning in this example. Alright, so let us now go back to the definition of limit. Let's recall what we saw in the previous video. So that means we again have sets like this. Okay, x is a subset of R and E is a subset of X. Then we have a real number x naught which is an adherent point of E. Also, there is a function, a real valued function f with x as its domain. And finally, there is a real number L. Then we say that f is, or rather f converges to, f converges to L at x naught in E if for every positive real number epsilon there exists another positive real number delta such that this implication is true, that if x belongs to E and the distance between x and x naught, x0 is less than delta, then the distance between f of x and L is less than or equal to epsilon. And one more minor thing, it does not really matter that we are considering strict inequality here and ordinary inequality here. You can use anything, okay? It does not make any difference in the end. And when this happens, we express this whole thing, entire thing, symbolically like this. Okay, so this is what we saw. We already have seen this. Now you can imagine one thing. I can write this condition slightly differently. And by differently, I don't mean I'm going to write something new, but I will just use intervals here instead of inequalities. So what the author is trying to say here is that although the definition is okay and we understand what it means, but it's still a little difficult to work with this definition in, say, trying to show that a concrete function has a concrete real number as its limit. But why? Where does that difficulty come from? You see, this condition can be rewritten like this. This one, if you want, you can write this one also similarly, or you can keep it as an inequality. It's up to you. But because we have less than or equal to, it will be a closed interval. So the difficulty here is that you have to verify that for each x belonging to this intersection, something else happens. Now, in such an interval, there are uncountably many x, uncountably many real numbers. And in the intersection also, you can imagine that in most of the cases, there will be uncountably many x. So, verifying something for an uncountable set, of course, is somewhat difficult. Okay, although when you actually want to verify something like this, you won't really have to work with each individual element separately. It's not like that you say you start by taking one x from here, then see whether for that x this happens, and then you take another x. It's actually not like that. But still I am saying that the extent or the amount of what can I say, infiniteness of this set of inputs makes it somewhat difficult. Now, can we reduce this amount of infiniteness? Yes, we can. We can bring down the uncountable infinity to a situation where we have to deal with only countably infinitely many objects. And we already know such an object which has countably many parts. They are sequences. So, using sequences, this entire thing can be rephrased, reformulated. So the next result is about that. We still have infinitely many elements to deal with even when we work with sequences, but still that is a countable infinity. That's the smallest size of infinity. So this is the next item. Proposition 938. So without actually writing any formal statement for this proposition, let us just see what the proposition says. So the beginning of the proposition is just like that. We again have sets like this. X naught is an adherent point of E. There is a function f which is real valued and it has x as its domain, and L is a real number. Then we have two statements which are logically equivalent. If any one of them is true, then so is the other. The first of them is this. That f converges to L at x naught in E. And the second, and this of course involves all those uncountably many points. But now the next one, this next statement involves sequences. For any sequence an in E converging to this point x naught, the sequence f of an converges to L. So what does this second statement say? It says that if you find a sequence an in E, and by that what do we mean? By that we mean that all the terms of this sequence, that is all the ANs, are elements in E. And it's not just any sequence in E, but it's a sequence in E which is converging to x naught. If you take any such sequence, then the functional values, if the sequence terms are the inputs, they give us a sequence which converges to L. So these two statements are logically equivalent. So here you see that in verifying this one, so this is also an implication. No? If there is a sequence in E converging to x naught, then it implies that this sequence converges to L. So there are only countably many real numbers that we are dealing with here. So that's why the size of that infinity is reduced, and hence the complexity is also reduced in some sense. Now the proof, of course, we won't do it here. It's an exercise. So we will do it when we solve the exercise. I think it's the first one. Yeah. You will find all these solutions in the community section next week or whenever its time comes. So for now we just take it as a fact. So we see that ultimately the limit of a function like this, what we already know, turns out to be the limit of a sequence. And that's why, because of this, we sometimes, instead of using this way of saying that is this language that f converges to L at x naught in E, instead of saying this, we say something like this, with which we are more familiar. We are more used to writing things like this, or expressing our limit in words, if I say so, like this, than this. This is unfamiliar. But now we know that we says something like this: because of this sequential formulation of limit, we have reformulated the notion of limits using sequences, and this is going to be very useful to us. Now there is a remark after this, and the remark points out one way in which we can use this equivalence. Now I think I messed up the number a little bit. Maybe the previous item itself was 8. Actually this is 9. Okay, sorry about that. So this remark is 10. It's the 10th item. And the remark just simply says this: with the notation of this proposition, proposition 939, if this limit exists and is L, and AN is a sequence in E. I mean, everything is what we have here, but if this happens and this happens, then the limit of f of AN is equal to L. This is one way in which we can use this equivalence. If we somehow are able to show, or by some means other than using this equivalence itself, by some means, some other means, we know that this limit is L, then for any sequence AN in E which converges to x naught, the limit of f of AN will be equal to L. Okay, so we will use this, actually we will use this somewhere. And this is why I said at the end of the previous video that the topology of a metric space is described by sequences. Sequences are enough to describe the topology. What this remark precisely means, let's just forget about that for now. We will see in due time. Okay, now there is another remark which is very interesting. Basically, this remark asks this: why this condition? Why do we need x naught to be an adherent point of E? There should be a reason for that, right? What would go wrong if x naught is not an adherent point of E? Then if this is the case, then you know that x naught is an exterior point of E. Exterior point of E, i.e. there exists a positive real number delta such that E does not intersect this open interval, so that the intersection remains empty. It's a situation like this. If you imagine the thing on the real line, say this is your x, x naught, and E is here somewhere, say E may be on this side also. So the point here is that around x naught you would find a region which does not have anything from E. The region isolates x naught from E. But now, under this condition, what happens to our limit? Let's see that the limit after all is an implication, right? And the implication is this. We are going to fully write the implication, but just let me add just some things first. Okay, so the implication is this: for every epsilon positive, there exists a positive delta. In order to distinguish this delta from this delta, let's just call it, say, delta prime, such that implies okay, so combine this with this and take delta prime equal to delta, and let's see what happens to the implication. Let's see how things look when we take delta prime equal to delta. And this itself, this whole thing is now equivalent to what? You see, we have already said that this intersection is empty. So that means now our implication looks like this. And this implication is vacuously true. Why? Because it's the hypothesis or antecedent of the implication is false. When that happens, we need not even know what the conclusion or the precedent of the implication is. In that case, it's vacuously true, but true nonetheless. So you see that by the definition of limit, in a very strange and weird way, the limit of f of x as x tends to x naught in E, now in our case, is actually equal to L, because the implication is true. But what is it that has gone wrong? Actually nothing has gone wrong, but now we can make things wrong. You see, because we need not care about the conclusion at all, simply the falsehood of our hypothesis implies that we have this. So in place of this L, you can choose just about anything. Any real number in our present situation will be a limit of this f of x. So the limit loses meaning at all. That's why we do not take exterior points and consider limits at those points. This is the reason why we should take an adherent point, so that, see, here there is no part of E that is close to x naught. We want things to actually be close to x naught and then see what happens to the corresponding functional values. Do they get close to some real number? If nothing gets close to x naught in the first place, then things are true, vacuously true, but it loses meaning and purpose, everything. Okay, so that's why we need this condition. Alright, so let's now move on. So it's not just merely a fancy thing to consider adherent point, it's necessary actually. And this next remark is extremely trivial, but nevertheless it is there. So let's see what it is. It just simply says that the variable that you used here, x, is a dummy variable. It can be given any other name also, nothing changes. That is, this limit, if it exists, is also equal to this limit. If you are calling it y, fine, they are the same. Okay, now because of the sequential formulation of limits that we have seen a while ago, we have a corollary, and this corollary tells us that the limit of a function, whenever it exists, is unique. Just like limits of sequences of real numbers are unique, limits of real valued functions are also unique whenever they exist. But just now we have seen that if we consider limits at points which are not adherent point, then that uniqueness, for example, is lost. So again, the same setup. We have these sets. X naught is an adherent point of E. F is a function from x into R. Then the conclusion of this corollary is that F has at most one limit at x naught in E. And the proof of this corollary, of course, is there. It's there in the text itself. It's not an exercise. So now we are going to see the proof. The corollary, of course, is going to use the sequential formulation, and that is why it's a corollary in the first place. So let me just give you the idea. I have quit writing things formally. It takes a long time and unnecessarily we see things, we have to wait. Just the main idea is what matters. So the proof goes like this. Suppose we have two real numbers L and L prime such that this is L and at the same time this is also L prime. If we are thinking very, what can I say, in a school-like manner, we may just say, okay, so this is equal to L and this is equal to L prime, so L is equal to L prime. No, you should understand what this thing means. It means all those things, okay. But what is telling us that all those things are not at the same time also true for L prime? Maybe that is the case. In spite of L and L prime being different, maybe. So we have to show that that cannot happen, that L and L prime then have to be equal. Alright. Now watch this. Since x0 is an adherent point of E. So you recall one result which says that in that case there will be a sequence in E that converges to x0, and that result is lemma 9114 by lemma 9114 there is a sequence an in E converging to x0. But you remember the remark that we had there, back there, what was the number of it? It was item number 10, 9310. That if there is a sequence in E converging to x0 and we also have the limit, then the functional values will converge to the limit. But we of course refer to the actual proposition itself. So by proposition 93, it's difficult to remember these numbers, 939. F of an converges to L because of this limit and also L prime because of this limit. But now we know that these are limits of a sequence of real numbers. So a sequence can have at most one limit, hence L is equal to L prime. If you want, you can refer here that result also, which says that sequences of real numbers have at most one limit. Whenever they don't have any limit, fine, and whenever they do, there is only one for each such sequence. And that's how we have ended up proving that there is at most one limit. Notice once more how this condition has played its role. Because x0 is an adherent point of E, there has to be at least one such sequence in E which converges to x0, and then we can use our sequential formulation. So the existence of this sequence comes from lemma 9140. And now finally we come to the well-known limit laws for functions, which correspond to the similar ones for sequences. That is, what do we get when we add two functions? What happens to their limit? It's about that. Or in other words, it's algebra of limits, if you want to call it. This is proposition 9314, and the author has named it limit laws for functions simply. So the beginning is just like what we have been seeing for quite some time. E is a subset of x is a subset of R, x0 is an adherent point of E, and this time we would need two functions, f and g are functions, real valued functions defined on x. If the limit of f of x at x0 in E exists and we call it L, and the limit of g of x also exists at x0 in E and we call it M, then the limit of, you can already guess what I am going to write, f of x plus g of x is L plus M. So that is the first one, and in this first one itself I can include another one also. If we subtract, then we have to consider the difference of the limits as well. Then of the maximum of f and g, you remember this function. This function is defined just like the other functions, pointwise. That is, the value of this function at x is the maximum among f of x and g of x, and it changes of course depending on x, and this is also equal to the maximum of L and M. Similarly, there is one involving minimum. Minimum of L and M. Then the limit of the product of these two functions is equal to the product of their limits and the limit of any real number times the function is equal to the limit times that real number, where actually you can see that this is just a special case of this, where we have one of the functions fine and the other function is the function constantly c. And all of these claims follow almost immediately if we use the similar algebra of limits for sequences that we already have, which I think is result 6119. For some reason I remembered that number, the laws of limit. And there is one more. Have I missed anything? Oh yes, there is that last one, which needs more condition. So we have all these things, and additionally, if G does not vanish in E and the limit is also non-zero, then the limit of this quotient is L over M. And the author has given a proof for only this plus case, and let me show you how easy it is. So suppose we want to prove this. There is a very subtle thing that I will say what it is. Let me just show you the proof first. Okay, so we have whatever we have in the statement. So the proof goes like this: let an be any, in order to say what that subtle thing is, after this proof is over, I am writing these things. Okay, let an be any sequence in E converging to x naught. Then, because we already have these two limits, we have these two limits. This is L and this is M. Note carefully that these are sequences. That's why limit n approaching infinity. And now after this you use the laws of limits of sequences. Then by although I remember the number that the law has, or laws of limits of sequences, but I forgot it's a theorem or proposition or whatever it is. So I just write start by this we have L plus N. So in this step we have used 6119, and this is just the definition of the sum of two functions, real valued functions. Now are we done? We are not done yet. You see, we have shown that if an is any sequence in E converging to x naught, then f plus g of an converges to L plus n. So by proposition 939, so that means the second statement B in that proposition is what we have shown, and since that statement is equivalent to A, so we can go to A from this and conclude this. If you can write f plus g of x, or you can just simply write this. And keep in mind that although those two statements are logically equivalent, but this is one thing and this is a different thing. But that's how you can imagine that you can prove all the other parts also. Okay, so we are not going to go into that. And now finally let me come to that whatever subtle thing I was talking about. You remember that we have also proved that the limit of a function whenever it exists is unique. In that proof, if you go back, in that proof you will see that since x naught is an adherent point of E, we recalled a previous result for the existence of a sequence in E that converges to x naught, and then we did whatever we did there. So such a sequence exists because x naught is an adherent point of E. That is not the case here. Here it's not enough to consider one such sequence. Here we want to consider any sequence, see, any sequence in E converging to x naught, and we want to show that the functional values, they also create a sequence that converges to L plus n, and then only we can conclude this. So you go back to the statement B of proposition 939 and note this thing carefully, that this has to happen for any sequence means for every sequence. It's not enough to just consider some sequences in E converging to x naught and show that for them the functional values create sequences which converge to the limit. No, this has to happen for every sequence in E converging to x naught. So that is a difference actually, and unfortunately this difference is somewhat subtle, and in one part the author has also made mistake. Okay, he messed up in one of the proofs. Not going to mention which one, it happens to all of us. So that's just it for tonight. After this also there are some discussion, so we will go through that next Sunday, and after that we will start solving the exercises. And our next upload is this coming Tuesday, and on Tuesday let's go back to exercises from Distel's graph theory. So it will appear in the community section, and one of you asked me to continue Herstein. So I think it's group theory or modules, I don't actually know, but that will happen only next Friday. Okay, but it will come back, of course, things cycle here. So that's just it. So see you on Tuesday in the community section with digital scrap theory exercises. Until then, this is me, Lucifer, from a mathematical group. Have a nice night.